Okay, welcome to the second session on complexity theory. So we'll begin with a talk by Erich Kaltofen on essentially optimal interactive certificates in linearity.
Thank you, Ketan. Thank you for the invitation to speak here. This talk, as I told Ketan, has geometry in it, but no complexity theory. And then he said, well, if the algorithms are optimal, it's complexity theory. So they're only essentially optimal. I wrote down here on the whiteboard that I allow myself optimality within a factor that is input size to the little o of 1. So this notation of having an exponent little o of 1, I will use a lot. And you have to think of it of having this factor in front of the complexity, that this may be a polylog. I learned this notation from Volker Strassen. I remember when he showed it to me at the dinner at a conference. The little o will, you can kill two constants, not just one. The big O constant and then also the exponent in the log. So, and in distinction to, I think, most of what was spoken here about, my complexity is bit complexity. So we heard about the matrix multiplication exponent, and then people say that this matrix multiplication exponent is in all of linear algebra problems, but it's not true. You will see. This was actually not the motivating example, but it is an example that brought in my co-author. I didn't mention my co-author, Jean-Guillaume Dumas. This is how he came on board. He's a person who builds linear algebra, builds a linear algebra library for exact linear algebra computation. It's called LinBox. And because we are on the web, we get these matrices sent to us from, this one was sent from K-theorists, and this is a matrix 2 million by 2 million, and they wanted to know the rank. So we could have cheated. We could have looked up their papers and seen what conjecture they made and just returned the value of that conjecture, but we didn't. We computed the rank in 1,000 CPU days. Then we gave them the rank, and they were happy.
Was that what they conjectured?
I don't know. So it's with a Monte-Carlo algorithm. We do not know a Las Vegas algorithm for computing the rank of a sparse matrix over a finite field. This is not known to us. And the question is, do you believe the rank? So what this talk is about is that I don't just give you the rank, I give you a certificate, and you can quickly in essentially linear time in your input size, verify that the rank is the rank. So the number returned is the rank of the matrix. So the motivation actually came from sums of squares, where we constructed ultimately integer matrices, large integer matrices. I'll show it briefly how you can get a proof for a polynomial inequality by two integer matrices, and then the proof is to prove that these two integer matrices are positive semi-definite. And that was the problem in which I formulated this notion of a certificate. At that time we didn't. I had a sort of a blind spot. I didn't look at interactive certificates. There is a soundness and a completeness assumption. The soundness is that the certificate cannot lie to you, and the completeness is that for every input you can produce such a certificate. And the assumption, of course, that we make today didn't make it then. I only said it had to be of of a lesser asymptotic computational complexity, the verification procedure, than it took to compute the output and the certificate. So today we are after essentially linear time certificate. So this is a bit complexity that is proportional to the number of bits in the input. Linear time. Now, the way you write it up in the proposal is that this is, of course, cloud computing. The cloud. We get the use of a Google data center for a weekend, and the data center computes something, and then we are able on our workstation in our lab to verify that what the Google data center produced is the correct answer. I added this for this conference because I'm sometimes asked by complexity theorists, isn't that Manuel Blum's programs that check their answers? It is not. The certificate has to be verifiable in a lesser complexity than you need for computing the output. They allow to rerun the program to check the output. So they have a rank certificate, but it would not be linear time, because they have to rerun the rank program on a modified matrix. That's what they do. But it is what I learned actually later, after we started these certificates. It is what Shafiq Goldwasser, Kalai, and Rotblum called the Muggles proof. So this is a notion where you do an interactive proof that the computation was performed, and you limit the prover in complexity. And I'll come back to this. I show you exactly what they did. So let's get started here quickly. My talk, Ketan, you should understand everything, not like what we discussed at lunch. So the Sparse certificates are not based on this, but all our certificates for dense linear algebra are based on this. This is Rusin Freivalds certificate, that quadratic time certificate for the matrix product. And this is a Monte-Carlo certificate. Yeah, what is the certificate? The certificate is the product. There's no additional data structure with it. And how does the verifier, how does Victor check that matrix C is the product of A and B? C multiplies the product from the right with a random vector, and he also multiplies. He is Victor. He is the verifier. So he also multiplies the C matrix from the right with a random vector, and if the two vectors agree, then with high probability it's the product. And actually, the Freivalds paper has another certificate to verify that the product of two integers is a third integer, which is also of better complexity than integer multiplication. So there has been a little bit of progress on this certificate. You can limit the number of random bits you need. The trick here is to choose your vector y, a random vector of consecutive powers, and then I've even written down the proof here, because then if you have enough such vectors, distinct vectors, not half of them can lie to you, because otherwise you would have the difference times the Vandermonde matrix to be zero, and that wouldn't be possible. So with that, we immediately get a certificate for non-singularity. So this is, again, I point to the whiteboard. We are talking about bit complexity here. So the matrices here are integer matrices. And the certificate that Peggy returns is a smallish prime. I gave this talk as a rehearsal in China, and they told me I should explain what I mean by smallish prime. So this prime is of a size so that you have a probability of success bounded away from 0, and that you preserve the essential linearity. So there is a trade-off. If the prime is too large, then you're no longer essentially linear. And if the prime is too small, you don't have a bounded away from 0 probability of success, that the output is verified. And it's just the LUP factorization. You see, you can by Freivalds, you can check whether this is the LUP factorization modulo P, and then the ln and the U will actually tell you that the matrix is non-singular. Singularity certificate is a little bit more interesting. So here you just expose a column relation. Trouble being that the column relation on an integer matrix can have n bits. So the column relation can have a number of bits that is proportional to the dimension of the matrix. So you have actually n squared bits in the column relation. And so you cannot perform the product. You cannot say A times the column relation, because this would cause you cubic bit time. So what you again do is you choose a smallish prime. You take the column relation modulo that smallish prime, and then check whether it's a column relation modulo P. And since Victor chooses that smallish prime randomly with high probability, this is a column relation for that integer matrix. So these are the immediate cases. Interestingly enough, they're not in Freivalds' paper. I checked it out. I thought this would be in Freivalds' paper already. So the first difficult one is rank. So you have an integer matrix, and you want to certify the rank with an additional piece of data in the output. And the first certificate we came up with in 2011 also used this LUP factorization, but now, of course, the P is given by Peggy, and so Peggy can cheat you by choosing a P where the matrix drops in rank, and you can prevent this by forcing Peggy to give you many such LUP factorizations modulo different primes. Now, to prove that you have a Monte-Carlo success with checking this LUP factorization, you need a linear number of primes. So this is a certificate that has cubic space, and it's not going to be a quadratic, essentially optimal certificate. But it's kind of funny because it has a lot of space, but you actually can randomly sample from that certificate. Victor can randomly sample a few such LUP factorizations, and he would get certainty that with high probability that this is the rank. But yeah.
Just want to be sure I understand the thing. So someone hands you a matrix with integer entries, and you want to know the rank.
Yeah.
And then someone performs this LUP factorization, and from that you read off the rank. And now you want to know if it's correct. And is at that point you reduce mod P? That's where
yeah. So this is a great remark, because you see, no, it's a good question, because the LUP factorization actually, the exact LUP factorization occupies cubic space. It's n cubed.
But I'm asking a very naive question. When do you reduce mod P?
Peggy reduces mod P. The prover.
Before or after factorization?
The prover reduces mod P.
The prover has to give you the matrices modulo P, because
The prover returns all this.
Okay.
You see, the prover also could do a rational LUP factorization.
I think instead of Peggy, you should say prover because mathematicians may not be used to this terminology, right?
Computer science.
I have psychological troubles far worse than that.
The prover.
Swallow Peggy much more than his.
Yeah.
So I guess you're supposed to trust whatever Peggy gives you.
No, you don't have to trust her because she gave you so many LUP factorizations that she can only cheat you on a linear number of them. So if you sample 5 times, you're going to hit a good one.
So you're testing her using Chinese remainder or something?
There's no Chinese remaindering here.
No, but how do you?
I mean, you have to.
How do you check that she's not cheating?
The proof, of course, that you separate yourself from 0 is by Chinese remaindering. So you have only a finite number of bad primes that drop the rank. So that's the proof. Yes, absolutely.
Questions related to PCP literature in some way?
That comes later. Okay. Yeah, I have a screenshot there. So actually, the funny thing is I posed this question to my colleagues in the symbolic computation community to reduce this to quadratic space, and for 2 years didn't get an answer, and I immediately I didn't know that I had this in between. Yeah, so this is a summary of what is known in terms of bit complexity for linear algebra objects other than the matrix product. So the rank, actually, to compute the rank of a matrix, it's of course, this is a Monte-Carlo algorithm. You choose a smallish prime. So you have this n, and I use omega for the matrix multiplication exponent, not the infimum here. So you have this matrix multiplication complexity, but only to the log of the bit length of the matrix. And then you have another quadratic term. This is a term. This is the number of bits you have in the matrix. So, ladies and gentlemen, please remember, if an integer matrix has long integers as entries, you can compute the rank in linear time of the input size, of the number of bits in the input. There's no...
Even without log factors?
Yeah, yeah, essentially. Every time I say linear, I mean essentially linear, yes.
Quasi-linear.
There's also... No, I don't want to say quasi-linear. I want to say essentially linear. This is Dan Bernstein's essentially linear. So, when the rank is small, you can do it in quadratic time no matter what.
So what is the terminology? N log n is called essentially linear?
Well, this is the number of bits you have in the input. The log of the norm of A, that's simply the length of the number of bits in the matrix.
And you still don't assume that it's a sparse or dense?
No, that's dense matrices. And this to prove that you can compute the rank of a matrix that has this lower rank in optimal time, that takes a little bit of work. That is not entirely obvious. Because you can't do LU factorization, it would be nonlinear.
So you're saying in this formula, if the norm of A is sufficiently large, then the term with the unknown exponent of omega will be less than
So yeah. If you have n-bit integers, if you have an n by n matrix with an n-bit integers, you do it in n-cubed time. Now there are famous results for us in the symbolic computation community for computing the determinant and the rank in n to the omega times the length of the input. So why is this famous? Yeah, because if you use Chinese remaindering, you get an extra factor of n. And it takes a lot of work to get rid of this extra factor of n. Arne Storjohan's paper has 54 pages. It's the most complicated determinant algorithm I know. All right. And he later also did it for rank.
The gain is Las Vegas. That's what is the
It's in Las Vegas. It's so for rank also, because Monte-Carlo would already be better, right?
So the answer is always correct, right?
It's when it's Monte-Carlo, the answer Las Vegas, the answer is always correct. Yeah.
And you can just do it into the like
Into the omega times the bit length of the input. Yeah.
So now this I really don't know. What is Las Vegas?
This is easy to explain.
What?
What is Las Vegas? I know what Monte-Carlo is.
Okay, so Las Vegas, it's always correct, but probably fast. So this the running time is expected. It could run longer.
But the answer will always be correct.
So any Monte Carlo algorithm where you can check the answer is a Las Vegas algorithm because you can run it again until you get the right answer. All right. So with Anna's rank algorithm, you get a certificate for the rank. You see, you simply run his algorithm. So the prover runs his algorithm, and when a matrix multiplication is performed on integer matrices, the product is stored. And that's the certificate. And then the verifier reruns the algorithm, reruns Story-Johan's algorithm. But when the algorithm has to perform a matrix multiplication, they use Freivalds. He uses Freivalds certificate to check whether this matrix product was performed right. So this is an essentially optimal certificate for dense matrix rank. It's still Monte-Carlo because the Freivalds check that the matrix product was performed is Monte-Carlo. So you choose a random vector, and with high probability, you detect a false product. So this is, you will see this is actually quite similar to Goldwasser, Kalai, and Rothblum. They do something very similar on arbitrary circuits. So what's the bad news? This is great news. I discovered this 2 days before the paper was due, and I put it in the last section as an essentially optimal rank certificate for integer matrices. So that's the good news. The determinant, we don't do this way, we do it in a much simpler way. But the bad news is the omega, this matrix multiplication exponent, cannot be achieved for all problems in linear algebra. We don't know how to do this. We do not know how to compute the characteristic polynomial in n to the omega times bit size of the inputs.
What are these other Greek letters?
So
1, 2, 3, 4, 5, 6, and 7 mean.
So these are parameters in this baby steps, giant steps algorithm, and the eta is the exponent that is achieved, for example, for the characteristic polynomial, and the characteristic polynomial has an exponent of 2.69.
Okay.
In bit complexity. And what's interesting also, I put this down for the complexity theory people, this is also the best known division-free complexity for the determinant. The determinant is a polynomial. You should be able to compute it on an arithmetic circuit without a division. And the best known circuit is larger than the circuit for matrix multiplication.
Why is it larger? It just matrix power. I mean, this algorithm, all it needs to do is matrix power. I mean, raising the matrix to the nth power. So the bit complexity increases, that's the point. Just so
This is exactly what it is. Our baby steps.
raising a matrix to the nth power.
Has n cubed entries. There's n cubed bits in the entries. You have n squared entries, and each has n bits. And actually, we do exactly that. We only go to a baby step. We only go to a square root of n power, and then we do a giant step and puzzle it together. That's exactly what we do. All right, so the upshot is,
How do you get it to n to the omega? I mean, you need n matrix multiplications. How do you get rid of that?
no, that,
Just log n.
Oh,
So yeah, so each one is n to the omega.
But he doesn't
You
even
pay
have
log
a-
n. If you didn't have to pay for the
B.
then it would be n to the omega times log n.
yeah. So this is Keller-Geric's characteristic polynomial algorithm.
Go.
The Keller-Gerich that's the algorithm. Yeah.
In this matrix, like what is 1, 2, 3, 4, 6, 7, and what is all this others?
Well, I only want you to look at one number, this one. So because this is the exponent that is achieved by these parameter settings, Joseph said, what do these parameters? So mean there is, of course, there is another exponent here. This is the exponent for rectangular matrix multiplication. So you multiply an n by n matrix by an n by n to the 0.30 matrix, and you do it in quadratic time. And that's actually Legal's exponent. I used to have Don Coppersmith's exponent here. So if you don't use fast rectangular matrix operations, you get a slightly higher exponent. But I just put this down because we don't know how to compute the Smith normal form of a matrix in that time in n to the omega. This is all in bit complexity. We are not at n to the omega. All right. So it has a consequence. What happened here? It has a consequence for the certificate I just showed you, because even if I had a quadratic time algorithm for matrix product, the certificate would be n to the 2.5. Because I would run our algorithm, but our algorithm for omega equal 2 doesn't have exponent 2. So I have a superlinear certificate. All right, we will be after the characteristic polynomial here, so that's what we want to do. I should say that I realized this, that somehow in this certificate where we had these many LUP factorizations mod primes, you could force the prover to choose the prime in a pre-agreed way so that the prover cannot cheat you. So for example, you could have a random primes generator that uses as its seed a value that depends on the matrix. And of course, this is a notion known from cryptography. This would be a public random function. You agree on a public random function, and then you also get an essentially linear certificate for rank. So this is modulo a public random function, because then you only have to inspect one LUP factorization mod P, because Peggy cannot manipulate P. All right, but this doesn't help us here. So I have another 20 minutes. So I will go over this rather quickly. It's actually funny that this is the next workshop on sums of squares and semi-definite programming. Why we are interested in the characteristic polynomial to start with. So this is what we want to do is we want to prove an inequality, a polynomial inequality that is valid for any real value of the variables. And this is just a note, this is for global optimization, so the global minimum is supposed to satisfy such an inequality. And you do it via sums of squares, which will lead you to positive semi-definite matrices. So I call polynomials positive semi-definite if they're non-negative, if they never attain a negative value. I actually liked Emil Artin's paper very much because he in his paper he writes for a definite form. For a definite form, he writes f is not less than 0. And this is just great because he doesn't write greater equal 0, he had not less than 0, because it's a rational function, so you can also hit the root of the denominator. I leave this here because this is a symbol that's not so easy to typeset in LaTeX actually. Well, not less than that. All right, so what we want to do is we want to use positive semi-definiteness of symmetric matrices. This means that the matrix, a symmetric matrix has real eigenvalues. A positive semi-definite matrix has no negative eigenvalue. And I have one screenshot. Oh, I'm sorry. And this, of course, can be tested from the characteristic polynomial. The characteristic polynomial, if you have a polynomial that has all real roots, you can count the number of positive roots and the number of negative roots by the Descartes rule of sign. Or here's the cheap version of the Descartes rule of sign. If you want to know whether a polynomial only has positive roots, you evaluate it at -x, and you have to get positive coefficients. And this is an if and only if. This is the Math 101 version of the Descartes rule of sign. So from the characteristic polynomial of this positive semi-definite matrix, we will be able to prove that matrix is positive semi-definite. That's why we want to have a certificate for the characteristic polynomial. So it comes from this fraction of sums of squares. So you can take a fraction of sums of squares and write it as a bilinear form where the vectors are vectors of terms. So, and the reason why this is an if and only if is because a positive semi-definite matrix has a Cholesky factorization. So you can go from this matrix identity, you can go back to the sums of squares. And what we do in our algorithms, we compute these positive semi-definite matrices via semi-definite programming plus a lot of other stuff, because it has to be an exact identity. This cannot be a numeric identity. But once you have an exact identity and have these matrices, you test them whether they're positive semi-definite. When they're positive semi-definite, you have a proof. So you can say this inequality is true. And the certificate is, of course, you give the matrix, you give these two positive semi-definite matrices, and then a proof that for the characteristic polynomial. And I want to do this in essentially linear time. So that was the motivating example. This is how I started thinking about this, because my collaborator, Li Hongxi, she said, once you have the SOS, you just square the polynomials and add them up. And that's the proof. And then we did the polynomials for the monotone column permanent conjecture. And so these polynomials occupy 10 gigabytes of space. And here's a proof for your case of the MCP. Not the MCP, it was Ram's problem. Check this 10 gigabytes, and this is completely unnecessary because all we had to do is give a proof for the characteristic polynomial of the matrices we constructed. All right, that was the motivation. There's a sums of squares example. All right, characteristic polynomial is the goal, and also sparse matrix rank. I will show you another protocol for sparse matrix rank. And unfortunately, I have to admit, I have no Monte-Carlo certificate. I only have a Monte-Carlo certificate when there is a public random function. So the use of the public random function is explained in the removal of interactivity of the proof of knowledge protocol. I'm looking at the time. So here I'm not entirely sure what the setting is with proof of knowledge. So let me just say this. So you've given the prover a V, and the prover claims that she has computed the discrete logarithm of that V. And you ask her to prove that to you. So what the prover does is they give you an H, which is another power of your primitive root base, and so she commits that H to you, and then Victor, the verifier, sends a random order, and then the prover will give to the verifier the linear combination of the discrete log and that random value that she has also chosen with a multiplier that is that C. And then the verifier can just check whether this identity is right in the exponent. And the reason why the verifier doesn't gain access to X is because discrete log is difficult, and this could be anything. So the verifier does not know R. Does not know R. So this is, we put this in. It's kind of completely disconnected from the talk, but.
Knowledge, because like from this way for example X modulo 2.
Yeah, it is in the same year that zero knowledge was first published. Yeah, so yeah, you're right. You're right. There is additional information. Yeah. But what interactive certificates? But we're actually not interested in this protocol at all. We're interested in how do you remove the interactivity. And the interactivity is removed by what I already had said before. You use this random public function, so the prover now also produces, like I did with rank, produces that coefficient that was used in the linear form by hashing on the values of the commitments. So this random function prevents the prover from cheating because there is commitment. And this is what we want to use. So I have it here for rank. So this would be the interactive protocol for rank. A one-round protocol. I want a half-a-round protocol, right? I don't want interactivity at all, because once the Google data center has computed this rank, they say goodbye. I don't want to have another question from you, and they're supposed to present the certificate. So you remove the interactivity simply by hashing, and this is what I said. You hash. The random smallish prime you choose, you hash from what the input is with a random function. Are there any questions?
I guess I have a question.
Yes.
I don't know crypto as well, but my understanding of the feature mirror is like a heuristic, right? So there's, in some sense, I mean, is this, prove these, because it depends on the strength, like the strength of
it. depends on the fact that you have a public random function.
Which is assumed to be cryptographic.
Without it, it's not true, actually. There's a proof. There's a proof.
Purely random function. Not necessarily.
Well, a random function in the notion of cryptography, right? Undistinguishable. The function is undistinguishable from a random function, right? This function here, this hash function, you cannot distinguish it from a truly random function in polynomial time. In the sense of cryptography. right, so now I can give you my certificate for the characteristic polynomial. One wonders why this took me. Well, it's actually Jean-Guillaume contributed to this because he realized that we should do interactive protocols. So you commit the characteristic polynomial, and then the verifier sends a smallish prime and the random value back to the prover, and the prover performs the certificate for the characteristic polynomial evaluated at that random value. You see, this is a certificate for determinant now, not for characteristic polynomial. And I've written down the certificate. The certificate is an LUP factorization modulo that smallish prime that the verifier has provided, and the verifier then just checks this LUP factorization with Freivalds algorithm, and it also has to check that the characteristic polynomial that was committed evaluates to that determinant that was sent back. I don't have much time. One has to think about it, why this is sound, why the prover cannot cheat you. And of course, the part is that if a wrong characteristic polynomial is sent, then you just the prover just cannot fake this determinant, because this is a certificate for the determinant. So there will be a disagreement in the evaluation of the characteristic polynomial and the determinant that is certified. And of course, you can take out the interactivity by Fiat-Shamir, by just hashing the smallish prime and that random value at which we evaluate from both the input matrix and the characteristic polynomial. This is important, the commitment of the characteristic polynomial. Because otherwise, the prover just adjusts the characteristic polynomial so that there is agreement at that R with the determinant. So this would be what you see here would be the certificate for the SOS proof. That's how you do an SOS proof. You have this matrix and you get this and you check it, then you know this polynomial inequality with high probability is true. Verification complexity is essentially linear in the input size. And again, the quadratic time comes in both evaluating this characteristic polynomial at this smallish random value and checking the LUP factorization with Freivalds. It looks so simple afterwards. Why did it take me 3 years? So this would be an interactive protocol for a sparse matrix rank. So it's very similar, except you cannot no longer do the LUP factorization because the matrix is sparse and the LUP factorization can become dense. So you use a preconditioner. So these Toeplitz matrices are preconditioners that put the product matrix into generic rank, as we say, where all the leading principal submatrices up to rank are non-singular. And then what we do is we certify that the R by R leading principal submatrix is non-singular, and we cannot do this with an LUP factorization. So you do this with a random right side vector, and you force the prover to give you a solution for the system. It's a smallish prime. It's not a small prime. So there's not. So you can control here the probability that this is right. And then you also need a certificate that the R plus 1 by R plus 1 leading principal submatrix is singular, and you do this with the column relation. So this would have been, this is for integer matrices. So actually, this would have been the certificate for this big matrix that I showed you at the very beginning. I have 5 minutes left. Yeah, here. It's if the matrix has a linear number of non-zero entries, you get linear time. I should say this maybe at this point. For sparse matrices, for matrices that have n to the 1 plus little o of 1 non-zero entries, the best algorithm we know to compute the rank, and the best algorithm we know to compute the determinant is quadratic in n. This is worse than for dense matrices. For dense matrices, even the cubic algorithm isn't really cubic, because there are n squared entries. What's even worse for these sparse matrices, that we do not have even a quadratic algorithm for computing the characteristic polynomial. The best algorithm is n to the 2.5. This is a super quadratic polynomial time algorithm. And I always ask people, Avi, what's the most famous polynomial time algorithm where the best algorithm is cubic in the input size? I don't know. There should be one, right?
You mean at least cubic?
At least cubic, yeah. It's not so easy. Ah, yeah, okay. Okay. All right. Okay. Deterministic primality test. Oh, yeah. Okay, yeah. All right, I want to say a little bit about, because I have 4 minutes left, about this PCP-based proofs of a computation. So this paper was brought to my attention. Actually, I went to Shafi Goldwasser's talk at Duke University, where she gives a Turing talk, and she had this in one of her screens, and so I asked her afterwards. So if you have an NC family of circuits, you can provide the verifier with an interactive protocol that certifies that the circuit was evaluated faithfully, and the verifier complexity is very small. It's essentially linear in the input size. Now, the prover complexity is of course the issue. We want to stay with essentially linear in verifier complexity, and then we want to bring the prover complexity down. And so their prover complexity was only polynomial in the complexity of the circuit itself, and this was improved for certain circuits. There's a restriction on the circuits to big O in the size of the circuits. And what's interesting about our construction is all our certificates can be provided with an additional little o of complexity it took to compute the output. So we don't even double the cost on the prover side. Now this is important to us. You see, if you have a gigantic sparse matrix and somebody comes to you and says, I can certify your rank, but it will take you 10 times as much, you might be dead because the computation already takes a month. So this is what their result is, and I have to admit to you that I don't entirely understand the proof. I looked at it. It is based even there's a protocol in it that I don't quite understand. The difficulty is not to verify each level of the circuit, but how you make sure that when you switch to the next level, there's no cheating done. So, but what is important here is that, this is of course true. This is an interactive protocol, say, for the problem we looked at the beginning, which was the rank of an integer matrix. It's an interactive protocol, but you can remove, I don't know how many rounds it has, didn't look at this. Actually, Thaler constructs multi-round protocols for the matrix product. Don't know how many rounds it has, but you should be able to remove the interactivity by Fiat-Shamir. So this is an alternate to what we were doing. Now, the flaw, this is my last, I'm out of time, but there is one aspect of this interactive protocol we don't quite like, which is, if the circuit, if you have a program to compute a determinant that has a bug in it, you will not uncover the bug with your certificate. Because the certificate will just be a certificate for the fact that you carried out the computation. So what we actually like in our certificates are certificates where the verification is independent of how the output has been computed. All right. Well, what's the consequence for algebraic geometry? In algebraic geometry, all computations are exponential in the number of variables. Is it true? I guess so, right? It's true, right?
I don't know what you mean by that.
I wouldn't sign this, so.
You wouldn't say it is true? You would.
Algebraic geometry, all computations are what?
Exponential in the number of variables, at least. It's asleep, so I cannot ask her.
Like the number of solutions.
Yeah. But you see, with this, you may be able, it's not quite true because it's also the number of inputs. With this, you may be able to certify it in polynomial time. You may be able to certify computation in polynomial time. And I think this is important because the computations are so complex. So if you run half a year, the certificate is then quick. So this is not so bad.
What you are describing is a very concrete method that one can use in practice, but this probably, I don't know, this theorem will be very...
So this here is the problem, right? You cannot afford to substantially increase the time of the computation to also get the certificate. The certificate has to come out with very little extra effort. I'm out of time, I'm over time. We have no certificate. I showed you a certificate for sparse rank. For the rank of a sparse matrix, we have no certificate for the determinant of a sparse matrix. Don't know how to certify such a quantity in linear time in the input. Don't know how to do it. But what also would be nice is if we would have a certificate for the characteristic polynomial that doesn't depend on this cryptographic assumption. You see, our rank doesn't depend on the cryptographic assumption. But the determinant doesn't depend on the cryptographic assumption. But the characteristic polynomial does. And I shall conclude. That's how I try to sell this work. So there is an entire area that is computer algebra and cryptography, where Gröbner is applied to breaking crypto schemes. So that field applies symbolic computation to cryptography. And with our certificates, we have gone the other way. We have applied cryptography do symbolic computation. Thank you very much.
Any questions?
So you, maybe a third of the way through, talked about certifying matrix rank.
Yeah.
And you said that you can do this using stored your hands algorithm, like by tracing.
Yeah.
Okay. And later.
Yeah.
This. And so then later then you talked about what you doing is later you.
I had an interactive protocol for it. Yes.
Yeah, but then later you went with the sparse rank of the sparse matrix.
Arne cannot do this now.
Sorry, the rank of the sparse matrix you cannot do. You had something. You had a slide on this later. Like you have the rank of a sparse matrix. You had the Toeplitz matrix. Your reconditioning. That was.
Yeah. Well, I should let you ask your question.
So my question is, does the Toeplitz preconditioning? Why does that not work for the dense case? Or does it? Like, because you presented two schemes, so and the Toeplitz one seems simpler to me.
Yeah, this may work. Yeah,
Okay.
yeah actually, yeah. But you see, for the rank, for the sparse rank, we have interactivity.
No, I understand that. I'm just.
So it works. It's quadratic. It's like Arne Stojohan's rank, but it makes that assumption of a public random function.
Sure. Okay.
So this is true. But you know, then you don't. For sparse, yeah, it's a good remark. Excellent observation. Because it didn't occur to me.
Any other question? Yes, thanks, Steve. Second talk will begin at 5 minutes.
Yes.
Yeah.